In a previous video, we have learned that integration of a rectangular region such as this can be carried out by iterated integral. Let's say this region is bounded by a and b on the x-axis and c and d on the y-axis. So integral such as this can be carried out as this, for example. Of course, we have proved this theorem when this function f of x is continuous on this closed bounded region. So this means first we consider this function as a function of x, then we integrate, and then consider the result as a function of y, then integrate over this. Next, of course, we want to extend this result to any shape. For example, in this, what about this kind of region? It's not rectangle, so we cannot do carry out integration like this. So, but before doing that, we consider a little bit easier problem where the region is sandwiched by two curves. So something like this. So this is, let's say, psi of x. So y equals psi of x, and this is y equals phi of x. And on the x-axis, it is from a to b. So in this region, how do we carry out an integration on this region? So this is sandwiched by two curves. Let's define this region more formally. So we consider such a region, which is a set of points on the plane where x is between a and b, and y is between some functions of x. And of course, we assume these functions psi and phi are continuous functions. And we also assume that the function we want to integrate is also continuous in this region. Okay. So we consider this kind of integral where the function is continuous on this region, and this region defined by this is clearly a Jordan closed region. So according to a previous theorem we have learned, this integral does exist, but we need to know how to calculate it explicitly, and this can be done by iterated integral, which we will see now. So first consider fixing the value of x in this interval between a and b, and consider the integral of this function. So this is now regarded as a function of y, and from this value to this value, phi of x to psi of x to phi of x. So since x is fixed, this has a fixed value. Of course, this is integrable. So we can define a function that maps a value of x to some real number. So this defines a function. So let's consider now this as a function of x. Now, and here's a lemma. This function, defined like this, is continuous on this interval. Of course, don't forget that we are assuming that this function f of xy is continuous on the Jordan closed region D as defined by this. Okay, under this assumption, the function defined by this is continuous on this interval. Okay, let's prove this lemma. What we want to show is that x1 of x, as defined by this, is continuous at every x0 in this interval. Okay, so to prove that, let epsilon be any number, any positive number. Real number. So of course we are actually assuming this is a very small number. And we are assuming that phi and psi are continuous. Continuous, so there exists a positive real number delta such that this difference if x minus x0 is less than, so x and x0 are close enough, then phi of x minus phi of x0 and also psi of x minus psi of x0, so they are arbitrarily small. So we can choose such a delta. Now let's define two constants, c as max of psi of x and psi of x0, and d as the minimum of phi of x and phi of x0. Okay, so what this means is that we are considering some closed region like this. So this is psi, and this is phi, and AB. So let's say this is x and this is x0, for example. So C is maximum of either this or this. So in this particular example, C will be so the maximum of this, so that would be this value. So this value would be C, and D is minimum of this or this, so minimum of this or this, so it would be like this. This value. So now we consider an interval between C and D. Okay. Then, so because these differences can be made arbitrarily small by choosing an appropriate value of delta, we have the following inequalities. That is f1 of x minus integral of c to d of fx and y dy is less than epsilon over 3, and also f1 of x0 minus the same integral, but the value of x is fixed at x0. Y is less than epsilon over 3. So what this means is that for this one, f1 of x means the integral of this function at x from this value to this value. And if you compare this integral with this, the second integral, that is between c and d. So in this particular example, they are actually the same. So it is obviously less than epsilon over 3 for any epsilon. And for this second case, we consider the integral of lowercase f of x 0 and y, so that integral is between this value and this value, so between the two curves, and compare that integral with the integral between c and d, so this part. So the difference between this yellow region and this red region can be made arbitrarily small if we choose the difference between x and x0 small enough. So if x is close enough to x0, the difference between this yellow integral and red integral can be made small enough. That's what these equations mean. And of course, that is possible because phi and psi are continuous. Now, note that this function f of x, y is actually uniformly continuous. Yes, on D, because we have seen that continuous function on a bounded closed region is uniformly continuous on that region. So we can define, let's redefine delta so that for all points x, y, and x prime, y prime in D, if x minus x prime is less than delta and y minus y prime modulus less than delta, then f of x y minus f of x prime y prime is less than epsilon over 3 d minus c. So if we define delta in this way, we can finally prove that the continuity f1 of x minus f1 of x0. So we want to show that this is less than epsilon, right? So this can be rearranged in this way. So f1 of x we subtract this integral, and add the same integral, and subtract the integral. Now it's the same integral, but changing the value of x, and add that integral to cancel. And finally, this one. So this is just an equality, right? We just add the same, add one term and subtract that term, and add another term and subtract that term. And now we use the triangle inequality. So split this part and this part and this part. So 3 parts. So that is not equal, but less than or equal. Plus. So for the second part, since the range of integration is the same, so we just put them together. But okay. And the last one. Okay, but the second one is actually we can put this modular sign to the inside the integral, so that will increase the value of this term. So let's wait a minute. So this one is, we have seen that less than epsilon over 3, and this one, the second one, is less than or equal to this integral. So we move the modulus symbols inside the integral. And the last one is also less than epsilon over 3 because of this. And wait a minute. So we define the value of delta so that this inequality holds. So we can now use this inequality, and if we use that, we have CD epsilon over 3 d minus c dy. But this is a constant, so we have an integration from c to d, so that will cancel this term. So we have this and this, and finally the epsilon. So this means, so just to summarize, so after all, we have shown that f1 of x minus f1 of x 0, the difference is less than epsilon. So this epsilon was any positive number. So therefore, this function f1 of x is continuous. at x0, and x0 was any value of x as long as it is in the interval between a and b. So therefore this function is continuous on that interval. And we are done. Now we know that this function f1 of x defined as this is continuous on the interval between a and b. So it is integrable. So f1 is integrable, and therefore we can define this integral of f1 between a and b. So that is integral between psi of x, phi of x, fxy, dy, and dx. So this is the iterated integral for a function defined on a region that is sandwiched by two continuous curves, psi and phi. Next, we need to show the next theorem. Okay, we have just seen that this integral is well defined, but it remains to be shown that the double integral, the original double integral of this function on the region D is indeed equal to this integral. Now let's prove this. First of all, we define a rectangular region, AB times CD, and these C and D are different from the previous C and D we used for proving the lemma, such that R includes the region D. So it would look like, so if we have region D, then this R would be something like this. And we define a new function, just like we've done before somewhere. Let's define f tilde of x and y as f of x, y, if xy is in D and otherwise 0. Okay, so on this part, the value of f tilde is same as f of xy, and in other parts, in this region, in these regions, the value of this x tilde is 0. Next, we define a partition delta, like a from a0 to a1 and so on up to an minus 1 and an, which is equal to b and c from c0, c1, and cm minus 1 cm, which is equal to d. So this rectangular region is split into smaller rectangles. So let's define dij as these smaller rectangular regions. Cj plus 1. And I varies from 0 to n minus 1, and j varies from 0 to m minus 1. And let's define these quantities mij as the supremum of the value of f tilde xy, where xy is in dij, and lowercase mij as the infimum. Where xy is in this smaller rectangular region. So that means if xy is in dij, then we have lowercase mij is less than or equal to f tilde xy, which is less than or equal to uppercase mij. So if we integrate these quantities with respect to y from cj to cj plus 1, we have cj plus 1 minus cj less than or equal to cj plus 1 f tilde dy and mij cj plus 1 minus cj. Next, we integrate these with respect to x from ai to ai plus 1. So we have ai plus 1 minus ai times cj plus 1 minus cj less than or equal to ai plus 1 and cj plus 1 dy and dx, and this is less than or equal to uppercase mij plus 1 minus ai cj. Next, we sum over these terms over I and j. So j and I, j. Of course, I and j varies over these ranges. So now this is just this, and this is just this, and this one. So let's consider this part in detail a little bit. So I from 0 to n minus 1 and j from 0 to m minus 1. ai plus 1 and cj plus 1. So we can move these summations, this summation, into here. So then if we add these, so this is partition of the interval between C and D. So after all, after summation, we have the integral from C to D. And similarly, after summation, this integral becomes an integral between A and B. So that's what it is in here. C, D, and A, B. Now, if we look at the leftmost hand side, that is this one, this term, this is actually the lower Riemann sum of f of xy. And the rightmost hand side is the upper sum of the same function. So upper Riemann sum. Riemann sum. And lower Riemann sum. Of this and this. And we know that this function f of xy is integrable. As we refine the partition, this term and this term converge to the same value. That is the double integral of f of x on the region D. On the other hand, by the definition of f tilde, we have this relation. So the integral of f tilde between C and D with respect to y is equal to this. Because outside of this range, between psi and phi, the value of f tilde is 0, so this equality holds. So if we substitute that and apply the squeeze theorem, we have the desired result. This is equal to this integral f tilde which is equal to psi x phi x dy dx. And we are done. Let's see a few examples. First, let's calculate this integral x plus y dx dy, where d is defined as this. X is positive or a non-negative, and y is non-negative, and x plus y is less than or equal to 2. So this means we are integrating the function x plus y in this region. So this line is x plus y is equal to 2, and this is 2, and this is 2, and this is origin. Okay. So this is a region that is sandwiched by this line and this line, right? So x moves from 0 to 2, and y, the value of y varies from here to here. Okay. In this case, this lower bound is happens to be a constant. So anyway, let's try to calculate that. So this integral can be calculated by using iterated integral. In this case, x varies from 0 to 2. And y varies from 0 to, so y, this line is 2 minus x, so 2 minus x and 0 dy and dx. So the first integrate by y, we get what is it, x times y and y squared over 2. So from y equal to 0 to y equal to 2 minus x. And that is, so when y is 0, it's 0. So let's see. That would be x times 2 minus x and 2 minus x squared over 2. And if you expand this, I think you should have 2 minus x squared 2x minus 2x x squared over 2. And if you integrate this, you have 2x and x cubed over 6 x from 0 to 2. And the result should be 8 over 3. Okay, next example, consider this region. xy and x is between 0 and 1 and y is between 0 and x squared. So consider integrating any continuous function on this region. So this region is this. So we have this 1, 0, and 1. So this curve is y equals to x squared. So x between this and y is between 0 and this. So the region is this blue part. Now, if we want to integrate any function on this region, f of x, y, then we could either integrate first with respect to y, then with respect to x, or this curve can be equally expressed as x is equal to square root of y. So we could first integrate and also y varies from 0 to 1. So first integrate with respect to x, but here from y squared to 1. square root of y to 1, then with respect to y.